My name is Jiali. The paper I'm going to present today is the value of price discrimination in large random networks. This is a joint work with Ankur and Zizhuo Wang. Let me first walk you through the motivation of our paper. Actually, this is a very straightforward story. In recent years, the use of social network information in marketing has become more and more popular. For example, some e-commerce websites, they might use some form of social information to provide personalization. For example, provide personalized coupons for different customers. However, there's some issue for this kind of marketing strategy because the lack of transparency in such personalized pricing can reduce customer satisfaction and also create customer mistrust. Okay. In particular, there's one particular form of marketing strategy that use the personalized that use the network information to adjust pricing decisions. For example, firms might want to identify the key individuals in the network and give them some higher discounts as compared to other customers. In recent years, there has been significant research in this area. We only list few of them here. And most of this research has been focusing on the computation of the optimal pricing strategies. However, we want to take one step back in our work and ask a more fundamental question. Is it really worthwhile to use such kind of network information to do personalization? In particular, we want to answer the following three research questions. What is the value of price discrimination for the firm? What is the value of network information? And what role does the network structure play in determining the value of network information? Hopefully, after this talk, you will have an answer for these questions. Now, let me first introduce our model. So at a high level, we are considering a monopolist who sells a single divisible product to a group of customers embedded in a social network. And we assume that there is positive network externalities for these products. And our model is adopted from the literature, and we assume that there are n customers in the network, where the G is the adjacency matrix of this network, and Gij denotes the influence of customer J on customer I. Then the utility of customer I has the following form, where Xi is actually the consumption amount of customer I. And if you only look at the first, second, and the last term of this utility function, this has the quadratic form, which is widely used in the economics literature. And the third term is actually the network externality term. So we can see that if customer J is a neighbor of customer I, and the more customer J purchase, then the more customer I will value purchasing these products. Because we are interested in the setting of large random networks, so we make a small modification to this utility function for the ease of scaling when we do some asymptotic analysis later on. We introduce a normalized term here. So for these positive network externalities, we use the spectral norm of G plus G transpose to normalize it. And we also introduce this rho as the externality coefficient, sorry, is not displaying here, but we require this rho to be between 0 and 1. Now, having the utility function for each customer, and we assume that each customer tries to maximize his or her utility function given others' purchasing decisions, and this forms a consumption game, and the consumption equilibrium can be given in the following way. And this is how the customers are going to respond to the pricing decisions they receive from the monopolist. And given how these customers are going to respond, we can formulate the monopolist pricing problem, which is just to choose the price vector that maximizes his own profit, whereas here C is the cost of the product. And it turns out that this is actually a convex optimization problem, and we are able to find the analytical solution. And in the literature, this is a well-studied problem. So the optimal price vector has the following form. At the first glance, it looks a little bit complicated, but if we look in detail a little bit, so this K vector is actually represents the Bonach centrality, and it is defined as this matrix inversion form. If we do the geometric series of expansion for this matrix inversion, we can see that this can actually represent it as a sum of some vectors. So for customer I, the Bonnet centrality is actually the weighted sum of number of walks coming to that customer I, if this G matrix is a binary matrix. And if we look at this pricing vector, we can see that it actually has 3 different components. The first one gives a common price for all the customers. The second one is the markdown, The second one is the markup a customer will receive because he is being influenced by other customers. And the third one is the markdown a customer will receive because he is influencing other customers. And if we plug in this P star to the profit function we have before, we can find the optimal profits of the monopolies, which has the following form. And again, if we do the geometric series expansion of this matrix inversion, we can find that this pi star is actually proportional to the weighted sum of number of walks of different lengths coming of the matrix G plus G transpose. On the other hand, if the monopolist is not allowed to price differently for different customers, or if he's only allowed to set one single price for all the customers, then we can show that the optimal uniform price has the following form. So all the customers receive the price A plus C over 2. And again, if we plug this P0 into the profit function, we can see that the profit of the monopolist under this optimal uniform price has this form. It's very similar to the form we have before, except that earlier inside the matrix inversion, we have G plus G transpose, but now we have 2 times G. And this is very important as we try to quantify the value of price discrimination. And another observation is that this pi 0 is proportional to the weighted sum of number of walks of different length in the network G. And we also want to point out that although the network does not play a role in determining the optimal uniform price, but it does play a role in determining the consumption equilibrium and thus the profits under the optimal uniform price. Now we are ready to quantify the value of price discrimination, which is defined in we define it in 2 different ways. The first one is called the monopolist regret, which is simply the absolute difference between the 2 profits we obtained before. And the second one is called the fractional regret, which is actually normalized by the optimal profit pi star. Now we have a way to evaluate the value of price discrimination. Let's first look at some simple examples to see. Okay, so one more point. So because in the optimal uniform price, we does not use any of the network information, so this value of price discrimination can also be viewed as the value of network information under our setting and our assumption. Now let's first look at some simple examples to see is there any value of price discrimination. For this simple directed line graph, we can say that it should be high value of price discrimination because Tom is influencing all the other customers in the network, but Alex is being influenced by all the other customers. However, if we simply add one directed link from Alex to Tom, then this is a directed cycle, and each customer has an equivalent position in the network, and there should not be any value of price discrimination. Let's look at more examples. So for the sake of time, I will just simply tell you the answer of whether there's value of price discrimination. The answer is no, no, yes, yes, yes. So we can see that for the first figure, this is a symmetric graph, and in the previous literature, other people have shown that symmetry is actually a sufficient condition for no value of price discrimination. However, we can see that here, customer 1, as compared to the rest of the customers in the network, they have a different centrality. So this example tells us that heterogeneous centrality may lead to the same price. For the second case, as we have mentioned before, this is a directed cycle, and there should not be any value of price discrimination. However, this is not a symmetric network, so asymmetric may lead to the same price. For case 3, if you look carefully for each node in this figure, you can see that it has the same in degree and out degree, but this lead to different prices. So same in degree and out degree for each node may give a value of price discrimination. And for the last 2 cases, for case D, it has homogeneous centrality based on the network G, and for case E, it has homogeneous centrality based on the network G plus G transpose. But none of these 2 give the same price. So homogeneous centrality may lead to different prices. And now, at the first glance, it looks a little bit mysterious whether or not a network will have value of price discrimination. Can we actually find a sufficient and necessary condition for this? And the answer is yes. Before doing that, we introduce a definition. A network is called price discrimination-free network if for any externality coefficient rho and any A greater than C that are positive, the value of price discrimination is 0. That is, the regret is 0 or the fractional regret is 0. And this theorem characterizes the sufficient and necessary condition for whether a network has value of price discrimination. It means that for each node and for any positive integer k, there is same number of walks of length k starting and ending at this node. A simple corollary of this theorem is that if G plus G transpose is actually a regular network, then G is price discrimination free if and only if the in degree and out degree of each node are equal. Sorry for the display issue again. Now, up to this point, we are looking at deterministic network. That is, given a fixed network, we know the adjacency matrix. We use these formulas to quantify the value of price discrimination, and we give the sufficient and necessary condition. The next step is we want to extend our setting to random network. That is, if the network is not deterministic, but it comes from some random processes, then the value of price discrimination will actually become also a random variable. Then how can we quantify that? To do that, we consider a sequence of networks indexed by the number of customers in the network. This n is actually the number of customers. And simple generalization of the utility function as before. And then for this paper, we mainly focus on a special class of random networks called the Adels-Renyi networks. To remind you a little bit, this network assumes that if there are n nodes in the network, then for each ordered pair of nodes, with probability Pn, the link between them exists, and with probability 1 minus Pn, the link does not exist. And we are interested in evaluating the asymptotic value of price discrimination for such networks. The following table summarizes our main results. It looks a little bit complicated, but I will come back to this later. So it basically tells us that under different network densities, we will obtain different asymptotic rates of expected regret and expected fractional regret. And all these rates are theta rates. That means that they are tight. And furthermore, we are able to show that given any sequence of network densities for the sequence of Adels-Renyi random graph, the expected regret is actually growing sublinear in the size of the network, and the expected fractional regret is vanishing asymptotically. To prove these results, we rely on analyzing the walks of different lengths in the random networks. For example, we need to provide a lower bound for walks in matrix G and upper bound for the walks in the matrix G plus G transpose. And also, we need to bound the spectral norms of the random networks, and we use some kind of classical results in random graph theory to show them. Also, to show the tightness of the results, we construct some special networks to make sure that the upper bound and the lower bound are matched, and therefore we can obtain the theta rates. Now, let me come to the discussion of our results. Here comes the table again. If you look at the first row of this table, we can see that when Pn is growing slower than 1 over n, then the smaller the Pn is, the smaller the fractional regret is. This is because when Pn is small, the network is very well fragmented, and there are a lot of small components in the network, which limits the impact of any individual to the other customers. And therefore, at this range of network density, the value of price discrimination is small. On the other hand, if the Pn is large enough, which grows faster than log n by n, then the larger the Pn is, the smaller the fractional regret is. This is because at this range, the network becomes more regular and behave more balanced, and a lot of cycles in the network can actually balance out the network effect and lead to a small value of price discrimination. In the middle range, we show that the fractional regret is around the largest. This is because when it is moderately large, giant components emerge, and also the cycles and longer paths emerge. Although the cycles can balance out some of the network effects, the giant components and also although the cycles can balance out some of the network effects, but the giant components and longer path, they are actually dominating the effect, and that's why the value of price discrimination is highest around this range. It will be more intuitive to show you some figures. We do some numerical experiments, and for the first set of figures, we look at the random graph of fixed size n equals to 10,000, and we can see that as the network density increase from the left to the right, the fractional regret first increase and then decrease with the peak at p equals to log n by n. What about as n grows large? We can see in this figure that, we actually do the numerical experiments and plot the average fractional regret in the log scale. And we can see that as the x-axis is the size of the network, as the size of the network increase under different network densities, all these fractional regrets are decreasing in n. And this confirms one of our previous theoretical results. We also realized that the adults running random graph are not good representations of some real-world networks, so we also obtained some real network data and try to compute the value of price discrimination in those networks. The results are summarized in this table, and we can see, if you look at the last 4 rows of this table, we can see that the value of price discrimination or the fractional regret is generally small for all these real-world networks that we obtain online. And this suggests that our results might actually be applicable to other types of network, and this can be one of our further directions. Okay, in conclusion, we study the value of price discrimination in networks. For fixed network or deterministic network, we quantify the value of price discrimination and give the characterization of the sufficient and necessary condition on whether or not the network will have value of price discrimination. For random network, we study the asymptotic regrets for adults running graph under different ranges of network density, and we show that the fractional regret is asymptotically vanishing. Also, the fractional regret is the highest when the connectivity is the modest. And there are much work to be done. For example, as I mentioned, we can study other types of random network and see what happens there. And this concludes my talk, and thanks for your attention. I'm happy to take any questions.
So when the graph is random, the regret is also a random variable.
Yes.
Are your results the expectation of that random variable?
Yes. Yeah, that's the table that I show here. They are all expected regret and expected fractional regrets. Yes.
How about prices? Do you solve price for each realization of the network, or do you solve it for the expected network?
In short, is for each realization of the network, we obtain the optimal price, but actually we cannot obtain that. So we assume that if there is a network realized, then what will be the optimal price and compare the differences between the profit. Yes.